es ist jetzt entwickelt. Draufbleiben, ja.
So, working? Hello? Yeah. Okay, welcome back. We are going to continue in section 2 with chapter 2.3, talking about H-curl and H-defined element spaces. I think these function spaces are particular strengths of NGSolve. We have H-curl, H-diff, a good zoo of elements in it. Give me a quick introduction. Okay, everyone knows the standard H1 elements, just nodal elements, point values in the vertices of the element. Many of you have seen Nedelec elements or H elements, H-curl conforming elements where the degrees of freedoms are now integrals along edges. H elements. Or phase elements, Ravier-Tomar elements, where the degrees of freedoms are now integrals of the normal component over the phases. And very easy, L2 elements are just piecewise constant finite elements, lowest order case just one value per element, denoted by this dot in the center. And it's good to not only look at these function spaces by itself, but look at them within the DRAM complex in a sequence. So if you have H1 functions taking the gradients, they go into H-curl. H-curl are functions, L2 functions, which curl is also well defined in L2. H-curl, you can build the curl, which goes into H-diff. To get the divergence of this H-diff space, divergence L2, it ends up in L2. And these finite elements, subspaces, which also satisfies this exact sequence here. And in NGSolve, we support these finite element spaces for H1, H-curl, H-diff, L2 of arbitrary order. So we have them on triangles, tetrahedral element, hexahedral, prisms, even pyramids of every order, and you can also map the elements. Okay, let's get a bit familiar with the spaces by looking at basis functions. Okay, importing everything. Let us first look onto the high-order basis functions of the H1 space. Play around with it a bit. Okay, I have a simple 2D domain, H1 space of order 3. Okay, now I want to look at basis functions like this here. So I have here the familiar head basis function. We can look at it as a graph, like this. Everyone knows this head function. Okay, I get this by declaring a grid function g of u, setting the whole vector to 0, but only entry number 17, I looked up before, this is vertex 17, set to 1. So I get exactly this base function related to vertex number 17. hierarchical high-order H1 elements have degrees of freedoms, basis functions on the edges. We have P3, so we have two basis functions on the edge. Let's look at them. Okay, I create a node ID for edge number 10, asking the finite element space for the DOFs associated with this edge. I have the edge DOFs on this. These are two degrees of freedoms, 39, 40, sitting on the edge number 10. And now I want to look at the two basis functions, 39 and 40. How do I do this? This is edge here. What is the deformation? Okay, you see a quadratic bubble function. So this is a quadratic function on the edge decaying into these two elements. And now we can look also on the other basis function, number 40, on this edge. This is edge of second entry. This gives us number 40. This is a function which is a polynomial of order 3 on the edge, going up and down on the edge and decaying into this element. So these basis functions are associated with the edges. The first one, the vertex basis functions, are sitting on the corner points, the vertices. And finally, with a third order triangular space, we already have interior basis functions. These are these bubbles here, a function living on one triangle being 0 on the neighboring, on the boundary of the element. This hierarchical concept gives us a proper continuity. Functions are continuous from one element to the neighboring element, what we easily see with the scalar elements. And this is very similar also for H-curl and H-diff. Okay, coming back to the coupling types, if we ask the coupling type of the DOF numbers, we see the first ones are wire basket DOFs, these are the vertex DOFs. Then the edge DOFs starting from 19 till 102 are living on the edges, the interface DOFs, and final ones are local DOFs interior into the triangle. Okay, similar H-curl. Looking at basis functions for the H-curl space. Here's the construction we have. For H1, we have the vertex basis functions, something on the edges, on the faces, on the cells. For H-curl, we have always this lowest order edge elements, I've said the sketch above, plus adding something on the edges, faces, and cells. And we know they are related by the gradients. So the gradients of the high order edge basis functions are the H-curl edge basis functions, and so on. And the particular thing in NGSolve, we construct basis functions. We just write down basis functions for H-curl, H-diff. A more classical construction is going via degrees of freedoms and then defining the basis functions via bioorthogonalization, but we directly implement the basis functions having the right continuity. Okay, declare an H-curl space, order 2. Okay, the edge DOFs of edge number 10 again. The first degree of freedom on this edge. This edge has degree of freedom number 10, 62, 63. Okay, this is now the basis function for the edge. And indeed, we are looking at the absolute value of the basis function. It looks better if we look at the, oops, I have to close and open it again. You see, if we activate vectors, I'm plotting vectors on the surface, the 2D domain. You can refine the vector grid. Okay, and this is the first edge basis functions. And we see this is, or we can, yeah, we see it if you know it. This function has a tangential component from one element to the other element. It is tangentially continuous from this element to the neighboring element, since the tangential component is 0 on this edge. So this H-curl basis function must have the right 0 tangential boundary components at the boundary of the support of the basis function. Yeah. And we can look also at element basis functions. something like here. This is a vector value basis function which has 0 tangential boundary component as a whole boundary of the element and is a second order polynomial. Okay, so the message is we have a very similar concept of basis functions for the H-curl and H-diff space. The precise definition of the basis functions you find in the literature, we give, for example, the thesis by Sabine Zagelmeier, you find in details how the basis functions are defined. H-diff finite element space, very similar. It's a vector valued space where the normal component is continuous from one element to the neighboring element. For H-diff, people are working on this, know about the BDM version, which are polynomials of a certain degree, and the Ravier-Tomar version, which are polynomials between the orders. So you have a Ravier-Tomar second order space. We have more than second order polynomials, but not the complete third order. And we always had the question, yes, now we have the Ravier-Tomar, precisely the Ravier-Tomar space, and we also have the first elements of the first type. To check this, okay, I define an H-diff finite element space over the 2, activating Ravier-Tomar. And I'm picking a function x times y times the vector xy. This is a third order polynomial, which is P2 times a certain vector xy, which defines this particular Ravier-Tomar space. I interpolate the H-diff space. I interpolate this function in my H-diff space, and I compute the interpolation error, the given function minus interpolated function, and see it's numerically 0. Okay, when you do variational problems, we have seen we can use the gradient of trial and test functions, gradient of u, gradient of v. What can you do with these H-curl or H-diff functions? If you can form the curl and the diff. So we can ask the derivative name of the grid function or of the trial function. The first name, the H1 function, tells us my derivative is called gradient. The H-diff function tells me its derivative name is divergence or curl. But you can do even something more. So for example, for H1 functions, the polynomials on the elements, you can also form second order derivatives. You can compute the Hessian matrix on the element. What is needed for some elements, for error estimates, for example. And also for some methods we will see later on, they use the H-diff function space, but we need the gradient on the element. Indeed, the H-diff space provides also some additional operators. So we can ask the H-diff function for its operators and see that it also can compute the gradient of the H-diff function. And the gradient means element-wise gradient. On every element, it's a polynomial, and from this polynomial, we compute the gradient. And we can plot it and look at it. Okay, we should look on it as a scalar function. This is now the 0, 1 component of the gradient of the H-diff function. Well, and people who know this for a while, they are smiling. How do we treat the gradient? Is it row-wise? Is it column-wise? It's not very consistent. And now we introduced a capital gradient. And the capital gradient is always the Jacobian matrix. So somehow to get rid of this row-wise, column-wise inconsistency, you can try now the capital-wise gradient. And it's a little math to check that the other one was the transposed Jacobian. Okay, this is the basis for these function spaces. In the next chapters, we will see some things we can do with this H-curl space. If we talk of H-curl, certainly most of you think immediately about Maxwell equations. What is the canonical application for H-curl? Solve Maxwell equations. Let's do an example with Maxwell. We solve Maxwell. Okay, we are looking just at magnetostatics, and the model should be a permanent magnet. Where you give the magnetization field M by a magnet and computes the B field, the H field, via a vector potential formulation. Magnetic flux B is mu times H plus magnetization, divergence free, curl H to be 0. We introduce, as usual, a vector potential, B is curl A, and put equations together, so we get the curl equation, curl A, and curl brought to the right-hand side. In weak form, it is to find a vector potential in this H curl space, satisfying this version of formulation, magnetization coefficient times curl A, curl V, in this right-hand side. Okay. Bringing up NGSolve. Okay, here we model a 3D geometry. Let's have a look on it. Nope. Why don't we see anything? Okay, sorry, let me restart. Yeah, now we see it. Okay, we have a box with a cylindrical magnet in it. We can model the box by, we can describe this by NetGen built-in constructive solid geometry. We have an ortho brick, give a boundary condition for the outer boundary. We have a magnet, what is an infinite cylinder described by 2 points and radius, cut with a brick again. Air domain is box minus magnet, so it's a simple CSG modeler here. We feed this into the geometry. We give names, material air, material magnet to the domain, and mesh it. Got the mesh also. Can clip inside. We can select the clipping plane to look inside. Enable clipping. Yeah, to look inside. Okay, pretty much the same as we had before. Define a finite element space. It's an H curl space, the mesh, third order. We give Dirichlet boundary conditions at the boundary element called outer. We specify this in the geometry. There's one flag, no gradients. So we have a basis function consisting of gradient function and other. We're doing only magnetostatics, so we can skip also gradients. Trial and test functions. Okay, we want to find a coefficient function relative mu r. And here you can see the nice Python syntax. So we are iterating over the materials of the mesh with a loop over magnet and air. And in Python syntax, so if the material is called magnets, then we get 1000, else we get 1. And we get a list of these coefficients. These constants and make a coefficient function out of it, which we can use in the variational formulation. By formula space, curl U, curl V. Okay, if you write down the Berliner form that everyone can see it, so you cannot hide your dirty tricks. So what we did in previous, so the matrix here is positive semi-definite. We always add some little epsilon to make it positive definite. That's what we're doing here. We're adding a little bit to regularize the problem. Modify it a bit to make the matrix non-singular. Okay, we define a preconditioner for it, BDDC, as Jay explained in the morning. It's a very generic preconditioner. The preconditioner must know what are the wire basket doors, what are the degrees of freedom, keeping everything together. These are now the lowest order edge basis functions. It knows the interface doors, which it breaks and makes continuous. And it knows the internal one, which can be condensed. Okay, 20,000 unknowns. Assemble the system and solve it. Okay. even in the tutorials, you find some different occurrences of the conjugate gradient iterates. So we have one conjugate gradient coming still from the C++ code. Now we're in a phase moving the solvers to the Python. This is now a Python implementation of the conjugate gradient iteration in the solvers module. It's still an ongoing process, and not everything is finally settled. Okay, we can look on different fields now. We can look on the vector potential A itself. We can look at the B field, the magnetic flux, Induktion, German. Or the H field, what is curl B, 1 over mu curl B minus magnetization. So you can write down this expression and look at these fields. How can we look on them? Visualization, I want to see the B field, for example. I can draw vector function in the clipping plane, so I get these small arrows. Can make more of them. Okay, like this. Maybe we want to do. Okay, that's fine. Or we can click on field lines. We have to enable field lines and select the vector field here, the B field. Build field lines. Yeah. Clip away a bit. Now we see these typical field lines from electromagnetic simulation. Okay, this was a very short Maxwell introduction showing how to solve a magnetostatic problem. Of course, you can continue doing eddy current problems by adding the conductivity, full Maxwell, frequency domain, time domain. For time domain, we have the time-dependent tutorials later on. You can do this in combination with Maxwell. And there will be a mini workshop on Wednesday morning by Carl Hollhaus doing more Maxwell examples with you, doing more exciting larger Maxwell examples. Questions on this section by now? We're still staying with Maxwell. There's a new section on a Maxwell eigenvalue problem. We solve the curl-curl eigenvalue problem. Okay, the curl-curl operator has a big null space. So if you set up this eigenvalue problem, you would have a lot of zero eigenvalues. That's the reason why we pose it not on H curl, but only in the complement to the gradient space. There it has a compact spectrum. And we use the pinwidth eigenvalue solver, which is built into NGSolve, similar implementation as we have seen before. But to run this and to treat this complement space, we have to connect it with a projection which projects out gradient fields by so-called Poisson projection. In a weak form, we're applying this operator. We compute the divergence, solve a Poisson equation, take gradients. If U is a gradient, so then this reads diff gradu Laplace, and we recover the same gradient again here. So we do an L2 co-projection to eliminate the gradients. Okay, we want to solve the Maxwell eigenvalues on the so-called Fichera cube, so a brick minus a smaller brick. We want to use higher order elements, and we want to do strong geometric refinements towards the edges of the geometry. So we mark these edges for singular edge refinement, the geometry with the singular edges, and we give two solids, and all edges in the intersection of these two solids are marked for singular refinement. If it's just a cube 2, then it's a cube 2, then all edges of cube 2 are marked for singular refinement. We get this by mesh refined HP, geometric HP refinement, 2 levels, and the grading factor telling how strong we move it. Okay, what we do here, H-curl space, A bilinear form, M bilinear form. Again, we have the preconditioner. The preconditioner should be for the shifted problem, so we need a regular matrix here. We have 30,000 unknowns. Okay, so as I mentioned before, the H-curl space is always related to an H1 space on the left and H-diff space on the right. If we can ask the H-curl space, what is your matching scalar H1 space? If you have one order higher, if you have variable order in the H-curl, the H1 has variable order as well. And it also provides us the gradient matrix. What is the embedding from the H1 into H-curl? It gives us a sparse matrix, the gradient operator from the H1 space into the H-curl space. We need this matrix to build the projection onto the gradient or the coprojection. And for this, we can now use operator notation. So the projection here is the identity minus the gradient matrix times the Poisson inverse times the transpose gradient, and we need the mass matrix here. So this operator, this matrix, this is a Python matrix multiplication operator. The meaning NGSolve that it does operator combination. So it first applies this matrix and then it applies the second matrix. So this is an inverse obtained by a sparse Koleski factorization, so we cannot really, doesn't really make sense to multiply these matrices together. It just composes the operators. Before we have some other multiplications. I say, here's a gradient mat is a sparse matrix. And from this we can create the transpose space matrix. Now these are all sparse matrices, and if we apply the matrix multiplication operator to sparse matrices, it multiplies them together and again gives a sparse matrix. Whenever it can make sense to multiply the matrices, it does it. If it does not make sense, then it does the operator algebra. You're having the gradient, having the inverse Laplacian. It's all in all 5 lines to form this projection. You have the preconditioner. We combine that with the projection, so we project in every iteration with a subspace. And this we put into the pinwidth solver. Running. These are the iteration steps of the pinwidth solver, very similar as the one you have seen before for the 2D Laplace problem. And we are computing, I think it's up to 20 iterations. You can check from the difference from the previous to the next eigenvalue how well the pinwidth already converged. Oh, sorry, I called the wrong. Yeah. And then we can look at the eigenfunctions of the mixed eigenvalue. Sorry. Eigenvalues. Okay, indeed, these are multiple eigenvalues, they are pretty close. These two are also multiple, these are a different eigenvalue. And the eigenfunction looks like this, so it's a pretty singular function, and for this it's good to have this very strong refinement towards the edges. With the max value, how to adjust it to 1. And you can look also at the different. No? Oh no, we have a different here. We have just one. Yeah. Sorry. I didn't have done this. No. Sorry, I don't know. We don't see the different one. Something wrong here, but it's. We see the first one, which looks sufficiently nice. Okay, what we have seen here is we calling a built-in eigenvalue solver. We're getting matrices. We can combine the matrices by this operator notation. If you understand the HB refinement. HDiff is always used for some mixed problems. Let's look at mixed formulations for second-order equations in here. So a mixed method is a method which allows to have exact flux conservation. What is produced goes through the edges. It has uses in a posteriori error estimates. And it's a model problem for many more complicated problems, like first-order problems, Stokes equations. Okay, we consider the second-order equation, the diffusion equation, as a model problem. Diff lambda cut u equals f with mixed boundary conditions. The standard primal formulation, we have the lambda in here. Source term, the natural boundary condition for the Neumann boundary condition. To get to a mixed formulation, we reduce it to a first-order system. The lambda inverse sigma is gradient u, and diff sigma equals f. Now the boundary condition can apply to sigma and to u. And we do now multiply now both of them, these equations by test functions to integration by parts. And we get now this one big rational formulation. We are looking for a sigma and u in a product space, HDiff times L2, with essential boundary condition for the normal component of sigma. All these terms added together with this right-hand side. Okay, first we set up a primal problem, H1. Okay, this gives us a reference solution. We want to compare this later on, so we do this with a bit higher order 4. There's the boundary condition at the bottom. Everything we know by now, nothing new, I think. Do everything by hand. Draw the primal solution and draw the primal flux. Now we're solving the mixed problem. This requires a finite element space for the flux variable, for the sigma, and HDiff space, and a second space for the L2 variable u, which is now L2. First is order flux. The scalar is one order lower. And for building the product space, we can make a finite element space built by a list of finite element space. It gives us the product space. We can ask it for trial functions and test functions. It returns tuples for the first and second components. Or we could also do the TNT to get a tuple of tuple. Normal vector coefficient function. The boundary conditions for the HDiff space is set only in normal direction. To write it down, we need somewhere normals. It is provided by the normal special coefficient function from NGSolve. It makes sense at the domain boundaries. And we have to give the dimensions with a 2D or 3D normal vector. Okay. Now, writing down the big binomial form, sigma times tau plus diff sigma times v plus and so on, the elements of the domain. Right-hand side is a volume term plus a boundary term ds. Okay, this was a design decision how to access the boundary values of the HDiff function. One could just, no, it's not implemented this way, but could implement it just by saying tau times normal, and everyone would expect that we take the full tau, or if we just access tau, one would have the full function of the domain at the boundary. But the boundary integrals are implemented only by degrees of freedom from the boundary, which allows us only to recover the boundary component from this. And to make it clear that we are talking about the boundary trace, we have to write dot trace. That we remind the Maths definition that the HDiff has only normal component trace. This gives us only the boundary values in normal direction. It's a vector, and if we dot it with a normal, we get a scalar. Okay, we declare a grade function in this space. The components are the sigma grade function and the u grade function. We just set the function something. We set the u to x and the sigma grid function, which is vector valued. We set the x component and the y component. What we see here, we see the u here, which we have set to x, so it's a piecewise constant field. The flux mixed is a sine 10x. Flux mixed 2 is the y component. Okay, we set now the essential boundary values for the HD function, the boundary, and using a BVP to solve the problem. And we should get the primal solution and the mixed solution. Very similar, look similar, but the mixed solution here looks not that nice. Of course, we only use P0 finite elements for the scalar u. For the flux, we have P1 for the flux for the mixed method, looking similar to the flux of the primal, but reminds that the primal problem was solved with order 4, so it's much more accurate. But this u, the scalar part of the mixed solution, is really not very good. It's piecewise constant. We can compute the error by just integrating the difference of both. We have the error in the u, and we have the error in the flux. But luckily, there are some simple post-processing tricks to recover also a more accurate scalar solution, like Arnold Pretzel here. This means we are solving local problems. We are computing a post-processed u hat, which is an element that's polynomial, discontinuous, such that lambda gradient u hat approximates sigma. That motivates this version of the problem. But we're solving a local grad problem, which is a constant kernel. So we have to constrain also the kernel by constraining the mean value. U hat and the mean value on the element the same as the originally computed u on the element. Let's prove this gives us a good post-processing to recover post-processed u of higher accuracy. This is set up again as a mixed problem, a product space for the post-processed u and the lambda Lagrange multiplier, one order higher. Lagrange multiplier is always piecewise constant. Write it down as a rational problem, solve it, and we see, okay, the error of the post-processed u is now much better than the original one, and it also looks better. Okay. The techniques how to set up mixed problems, how to do this post-processing, which come in several of the following exercises. Okay, many of you are interested in Stokes, Navier Stokes. This is now very basic, some standard discretization for the Stokes problem. We have this channel with a cylinder here, which is a circle, there's this obstacle in here. The first example, we use a simple Taylor-Hood element pairing, second order for the velocity, first order for the pressure, product space. We have trial functions ux, uy, and pressure, test functions, can form the divergence, very elementary here, taking the gradient of the ux serial component, write down the Stokes bilinear form. The boundary conditions very similar for the first component of the grid function, very much as before, and solve. And when you want to do Stokes, or when you want to do it in classroom or research, you want to try different discretizations, different pairs of velocity and pressure finite element functions. So I set up a full Stokes solver, provides a function space, it discretizes Stokes, and look what's coming out. Okay, let's try it with a higher order Taylor Hood. Fourth order for velocity, third order for pressure. And sorry, I did not execute this cell. Okay, just visual inspection and it looks good. Okay, let us try P2 for velocity and discontinuous P1 pressure for discontinuous P1 elements for the pressure. And if you remind your numerics classes, try it. And we come back that this is an unstable pair, and Umfbach was so kind and finds that the matrix is not invertible and was complaining that the discretization did not give an invertible matrix. This is a rather bad implementation, but it's an unstable element pairing. What's working are P2 plus elements, which means P2 elements plus adding a cubic bubble, making it P3 internally. Pressure discontinuous P1. We get this by defining the V space in H1, second order, but then we can manipulate it. We can set the order of node types, the different order. So we set the order for all triangles to 3. This means the internal element node have order 3 for the whole mesh. We are enriching the velocity space. Pressure space in L2, this was linear, and this works. Very similar, the mini element order 1 with a cubic bubble, working but not that nice. Okay, so what we had here is a compound space of 3 components, an H1, and a space for the pressure, H1 L2. And we are doing the work twice for the first 2 components. And for this, we have a vector H1 space, which tells us it has 2 components, which are the same finite element spaces. And it can optimize operations, and it can simplify the syntax. So the trial functions are now U and P, where U is already a vector from the vector H1. You can say anything about grade U, grade V. People here don't worry whether it's row-wise or column-wise, or you could write capital grade U times capital grade V, and you know it's a Jacobi matrix. This also provides a divergence. You don't have to do the x derivative for the first component plus the y of the second. And you get the same. You can also build block matrices. You can build the A block for Stokes. You can build the B matrix as separate matrices and combine them to a block system. We have the space for the V for the velocity, pressure again. Now we don't make the trial and test function of the product space. We don't have a product space here, just making trial and test from the first and the second. Now A is a binomial form living on the first space. It's grade U, grade V. I use the new grade. The B binomial form is now a form living on 2 different spaces. You give a trial space and a test space. You define the integrals with trial function from the first and test function from the second space. And this will assemble a rectangular matrix for you. We want to run some block preconditioner. For this, we need also some matrix for the pressure preconditioner, just an L2 here. You find right-hand side, solution, grid functions, set the boundary conditions. Okay, and now we are building, now we have the individual matrices. Now we are combining them to a block matrix. So K is now a block matrix with the matrix of from R in the upper left block, the B matrix transpose in the upper right block. We are not calling create transpose, we are not calling to generate a transpose matrix. The dot T property just flips multiplication and transpose multiplication. So it keeps the same matrix, but whenever we multiply this multiply vector, it does the transpose multiplication. A non means zero matrix. For the preconditioner, we build also a block matrix where we take, for in the simplest case, just the inverse of the A matrix. We could use an H1 preconditioner here, a block diagonal preconditioner, the inverse of the mass matrix for the preconditioner for the second part. Wraps the vectors from the right-hand side into a block vector, so the vectors are kept in memory. The block vector just points to the two vectors. The same for the solution. And we can call the min. So we have a saddle point problem, which is not positive definite anymore. We cannot conjugate gradients, but we can call min res, for example, for this block matrix K and the block precondition C. And I should get the same solution. Some questions to this section? Then let's continue to facet spaces and hybrid methods. The problem with this mixed Ravier-Thomas system is that you have to solve a saddle point problem where you could also solve a positive definite problem, what is much nicer. And with this hybridization trick, you can reduce the saddle point problem to a positive definite problem. What you do here is you break the continuity of the HDiff elements and reinforce it again by Lagrange multipliers. You start this by making the problem looking more complicated, introduce a search space, U hat, which are polynomials living on the individual edges. I know some people are experts in this and they immediately recognize this system. Some have not seen it before, so it's a bit tough. So I only want to bring it conceptually. So you have the U hat variable as a polynomial on the edges of the discretization of phase in the 3D. Same right-hand side as before. We're breaking continuity of the HDiff space now. The same element basis functions, but not constrained over the edges. For a long time, you could do it by setting the discontinuous flag to true. We have added it to a few spaces, and someone forgot to add it, and then we have a new space and not added the discontinuous space flag. Now we have also a discontinuous wrapper, which we can apply to every function space, also to H1 space to make discontinuous H1 space. Whatever function space you have, apply discontinuous, and it will not have the constraints on the vertices. So it will duplicate the degrees of freedoms for every element. Okay, if we try this with or without, discontinuous true, then 80 degrees of freedom, discontinuous false, we have less degrees of freedom. Okay, disadvantage, we have more sigma doves, but the positive side, they are now poorly local, and we can get rid of them by static condensation. We can condense out the sigmas, we can condense out the original U, only the new facet variables U hat are remaining. New concept here is also that we need integrals over the faces, which we rewrite as integrals over element boundaries. This here is a new term. So we are integrating over element boundaries. So we say dot dx of element boundary true. It's still a loop over the volume element, so at dx, but on the element, it does not integrate over the volume of the element, but of the boundary of the element. Sigma dot n is the same normal vector we defined before, but from the context, it's now understood as being the normal vector on every element. Okay, I said condense false here. Right-hand side is before. Okay, assemble. So if we can condense, we do this. If we cannot condense, we can only use a direct solver. We get into the second branch. But the interesting part is if we activate condense, make condense to true, we're looking at matrix entries. The final assembled matrix has now 6,000 entries, while without condense, oh wow, the matrix had above 70, 10 times more. Matrix entries. And now if with the condense system, it has only degrees of freedom sitting on the edges or faces, gives a positive definite matrix, so we can use a conjugate gradient iteration. Harmonic extension, as we have seen in the static condensation chapter, recovers now the U and the sigma variable inside. Okay, it's a very interesting old trick. Going back to the 60s, and very easily implemented also in NGSolve. Another discretization method, discontinuous Gajerkin methods, or hybrid DG. Okay, what is the idea? So we're using piecewise polynomials, discontinuous functions, to discretize H1 type equations, which would require continuous finite elements, but with DG methods you can use discontinuous one. Okay, nice that we can do. One advantage is that we can use upwind stabilization techniques if we have convection-dominated problems. If you have a flow over an edge, we can pick the upwind side of the edge and treat boundary integrals with upwind. Okay, these are all the terms, as you have seen it before. With DG you have boundary integrals and jump terms. If you have a convective term, you have element integrals of the first order derivative plus a facet integral with the upwind u, either taking from the inflow or from the outflow boundary of the element. So always from the upwind side. Okay, one disadvantage of DG is you have to look into the neighboring element. You need basis function from the neighbor element, which are not defined on the current element, interact also with the basis function on the current element, which leads to a larger matrix graph. And we are building the matrix graph in advance, so we have to tell that we need a larger matrix graph by setting DG jumps to true. How to specify these terms? We will need a jump u. What is u minus neighboring u, my u minus u, other u. Okay. For these skeleton terms, we have a loop where we are iterating over the edges of the mesh. One element is chosen as the master element, which has the normal vector as outgoing normal vector. The other side is the other element. And we can refer to the trial function on the other element by u dot other. So the jump is current element minus other element. Similar, we need the mean value of the gradient. And we have to set the skeleton flag for the integration over the mesh skeleton. And we say dx skeleton we iterate over all edges inside the domain. And if we set ds skeleton, we are iterating over the boundary of the domain, which is typically used for the boundary conditions. Here you find all these terms you have seen in the planar form before. Now I define a diffusion as a sum of integrals. It's an element integral, element or a skeleton integral, and sum of integrals of different types. I'm feeding now the sum of integrals to the planar form, assemble it. Now, solution looks very familiar. Okay, but if you look at the number of non-zero entries in the DG matrix and you compare it to the number of of matrix entries, if you have a simple L2 planar form, you see much more matrix entries. Okay, no advantage for the Poisson equation. But now we are going to solve a convection diffusion problem. We are defining a wind function. Let's say it should blow in 20 in x and 5 upwards. In the planar form, we need now the upwind u upwind, which now depends on the direction of the wind. If it's going outward, if wind dot outgoing normal vector is positive, then it takes the value of the current element. If the wind blows inwards the element, then we take the u from the other element. With the if pos, we can build a decision whether the wind dot normal is positive or negative, either takes this value or that value. So it's like a tertiary operator in C. And this if pos will also go into the expression tree, will be passed over to C, and whenever we are in an integration point, it's an integration point we choose which u we're putting in. Now we have already the diffusion from before, plus additionally the convection terms, we feed into the convection diffusion planar form. Yeah, and you see the wind going to the right, to the up, blowing everything. There. Okay, maybe I go fast over this. So you can also hybridize the G methods. So introduce also facet variables on the skeleton, which has the advantage that you don't have to look into the neighboring element. From one element, you have to look only at the boundary of the element. Everything looks very similar, except that you are saving a lot of non-zero elements. You can do a static condensation. It has a lot of numerical advantages, that you condense out the interior of the element, reduce the problem to the skeleton again, as with the hybrid mix method, and you come much faster to the solution. And prepared also some spying the patterns of the matrix. It should pop up if I push again. Okay, what do we have? Ah, yeah, this is the pattern for the upwind matrix, which is only on one side, but here are the reserved entries. You can look into more details if you like. I'm going quickly over it. Okay, this is the way how you can specify DG or hybrid DG in NGSolve. You will see more on this in the Stokes, Navier Stokes section, where you see how it makes sense to discretize Stokes with, for example, HDIF conforming DG elements in the part by Christoph. Very shortly, we can do fourth order problems like Kirchhoff plate models, biharmonic equation. Mechanical engineers are more interested in this. We can do plates, and now we can also do nonlinear shells with this technique. The nasty part is that you do not like to implement C1 elements. We don't have C1 elements which would be needed for a conforming discretization of these H2 conforming problems. But we have two offers, two possibilities how to discretize these fourth order problems. One is the zero continuous DG, where you use continuous finite elements and you treat the missing continuity of the normal derivative by Facet, by DG or by hybrid DG methods. You do it hybrid DG wise, you introduce a new variable for the normal derivative. and the terms are very similar, and it's very similar as in the scalar DG case. A second very interesting method, which we like now very much and which we recommend, is the so-called Herland-Hammond-Johnson mixed method, which is a mixed method introducing a new flux, the moment, the sigma as a new variable, setting up a mixed method, in concept very similar to the mixed method for Laplace, in the details quite more advanced. For this we have now a matrix-valued function space called HDiff-diff, which are matrices which have continuous normal components. Building up a mixed method, terms very similar, and you can solve fourth order problems with it, which is more efficient as which is a pretty old method, rarely used, but if you count degrees of freedom, coupling degrees of freedom, it's an order better than a hybrid DG method. I'm very quick on this section, just to show that it's also in the tutorial here. I'm happy to discuss this in more details later. The last two sections in this chapter are new. People were always asking, okay, how are the degrees of freedoms? And we said, okay, no, we don't have degrees of freedom. We just write down the basis functions. So we write the basis function, set up the observational problem, do some projections at the boundary, and for most things this is enough. At some point, I think it was Michael Neuenteufel, we came up that we need some projection to some fun in spaces, and we started also developing the concept of dual basis functions in NGSolve. Let me introduce it by the standard interpolation operators. If you have some function u and you want to interpolate it to your finite element space, how do we do it? Before Jay was explaining, we have some very generic concept, just doing element-wise L2 projection and then averaging. This is simple, works always, is fast. That's what we do with a set. But at some points, you want to have some more sophisticated interpolation. The gold standard interpolation operator is this one. First, interpolate into the vertices. Pick your values in the vertices. Then you have some freedom on the edges and choose some moments, some test functions, to define the degrees of freedom on the edges. This is a variational problem on every edge of the mesh, integrating the finite element function against some polynomial test function to be the same as the input against some test function. And finally, we have basis functions inside the element, which are also set by testing against some moments. Okay. Let's first have a look to the standard set. We have a third order space. I have here a fourth order function, which does not fit into the space, so by interpolation we make some error. I have a very coarse mesh here. The autoscale does not work properly, so it does not only compare midpoint values, so I have to do manual scaling. We see it goes from 0 to 1. But if you look at the coefficient vector, the first four values are the vertex values, which should be 0 or 1 on left and right boundary, but they are only approximately 0 and 1, so they're not exactly preserved. This is where people started complaining about why don't we have the boundary values exact. With the dual operators and this canonical interpolation, you can do it. Okay, here we need integrals over the elements. We need integrals over the edges, the boundary of the element. In 3D, we need the cells, integrals of the faces, the boundaries, integrals of the edges. What are the codimension 2 elements, or the boundaries of the boundaries, and also the vertices, which are codimension 3 nodes. which we consider as the boundaries of the boundaries of the boundaries. Okay, and we're now just discretizing this definition of this canonical interpolation operator. Integrating u times the test function of the element, dx, element integral. U times test functions on the edges, where we say dx, element volume or boundary is boundary, and it integrates over the faces of the boundary of the element. Then we need also integrals of the codimension 2 boundaries, which we call now B boundary, and codimension 3 are BB boundary. Okay, so here we have these 3 integrals, where we apply the u, okay, and the dual basis functions, which we get by the dual operator. So if we have a test function from some finite element space, it provides us with a dual operator, dual basis functions. And this sees now whether we are integrated over elements, and it takes the test function from the element. If we are integrating over the boundaries of the element, it takes the polynomials from the boundary, and so on. So it selects the test functions, either this or this test functions, by knowing whether we evaluate integrals on the cells, codimension 1 cell, codimension 2 subcells. Okay, by this we can set up a variational problem, a matrix, a right-hand side, solve it. A picture, it looks similar. If we look at the values, now the vertex values are exactly 0 or 1. So we are interpolating in the vertices exactly. Okay. But the evaluation of this was now expensive. We were setting up a problem, inverting the matrix, but it's too expensive. I have to evaluate it twice to get the picture. Okay, if we spy the matrix A, we see the actual non-zero entries, and we see it's essentially a triangular matrix, a block triangular matrix. Only the diagonal blocks go to the upper right. But we have the first 4 rows are the vertex degrees of freedom and vertex test functions. This means I say decoupled problems vertex by vertex. Then we have block diagonals, edge by edge. So interpolating on every edge is decoupled. We can do it independently edge by edge. But the values we got on the vertices influence the values we get on the edges. So it's not a block diagonal, but a block triangular matrix. But we can solve very efficiently with this matrix by applying a proper Gauss-Seidel smoothing. If we sweep over the matrix, block by block by block, we have a direct solver just by Gauss-Seidel smoothing. This we're setting up next. The but is, we give smoothing blocks to the Gauss-Seidel, then this runs in parallel, it does reordering of the smoothing blocks, and it does not respect our triangular structure of the matrix. So we have to do this smoothing in 3 steps. First, we're doing the smoothing for all the vertex values. Okay, we're looping over the vertices of the mesh, asking for the dots in the vertices. These are also our blocks for the first block smoother. Can we do block Gauss-Seidel at all edge blocks and on all face blocks? Okay, we can print them. So smoothing blocks for the vertices are just the vertex degrees of freedom, then the 2 edge degrees of freedom of every edge, and for the element. Creating a smoother is indeed a solver for these block diagonals. Just doing one smoothing step solves the whole system. Okay, interpolation, okay, nice. Maybe some applications. One application we have here is that we can embed function spaces. Let's say you have an vector H1 function, and we want to represent it by an HDiff function. Interpolate from one finite element space into the other. These dual functions, you can do this. You can define the interpolation procedure from one space to another. Just write some finite element function space to the right-hand side where you had the function to be interpolated before. And now we can assemble a matrix on the left side, the matrix we had before, and assemble a matrix on the right-hand side. And then the left inverse times the right-hand side gives us a transfer operator from one to the other. Okay, what we have here, we have a vector H1 space and an HDiff space. We set the H1 function to something, and we want to interpolate this function into the HDiff space. Okay, we have two matrices now. The coupling matrix, which is rectangular, with the trial space H1 and the test space from the destination space, and the matrix to be inverted, which is a square matrix. Dual operator, the same left-hand side matrix, AHDiff, the mixed matrix with its dual functions on element integrals and element boundary integrals. Now we remember the HDiff has just degree of freedom on the element and the edges, no codimension 2 degree of freedom. We have just two terms here. We have two matrices, and the transformation from one space is the inverse of the first one composed with the matrix of the other one. Applying now this transformation matrix maps an H1, embeds an H1 function into an HDiff function. And both of them should look the same. One is the H1, this is the HDiff function. Okay, so these dual operators are a pretty new concept in NGSolve, coming to space to space. Big thanks to Michael Neunteufel, who has contributed most of these dual functions. We can define now also a matrix which provides this embedding from one space to the other as a mult function. So the mult of this matrix is doing the smoothing for vertex doves, edge doves, face doves. Why we do the matrix here? This can also define the transpose matrix operation. We need a transpose for the embedding, and sometimes we need the transpose of the embedding. One important application of this embedding of spaces is preconditioning, auxiliary space preconditioners. Assume you have one very fancy, complicated discretization with some fancy matrix valued elements, and you don't have a good preconditioner available. Hybrid does not provide a good preconditioner for HDiff function spaces, something like this. And you have a good parallel preconditioner for a simple H1 space. And then you can now build preconditioners by embedding the simple space with a simple discretization into the more fancy discretization, which gives you a good preconditioner for the advanced discretization. What gives you a good method for many different applications. I have here a very simple example where we have an H1 space, where we have plenty of preconditioners, and we have a DG discretization of an H1 problem. We want to use the H1 preconditioner, embed the H1 space into the discontinuous Gaussian L2 space. Okay, set up a DG discretization, set up an auxiliary H1 discretization, set up a transformation operator, either the one from above, but if we are going to L2, we have also built-in conversion operators to L2. So the H1 can provide a conversion operator to convert the H1 function represented in an L2 function space. Here we write down the auxiliary space preconditioner. We have the H1 preconditioner, and transform the H1 functions to L2 functions, space transformation, the transpose. But since you have only a subspace, you don't reach the full space, you have to combine it also with a local smoother, for example, a diagonal matrix. Okay, not 10 iterations, but you get the problem solved without doing much work to get the precondition for the DG discretization. Okay, these were pretty new dual bases in NGSolve. It works now for, Michael, H1, HCurl, HDiff, HDiff, L2, variable order, but yeah. Okay, last section is on matrix-free operator applications. There were also examples of this for a long time in the C++ code and some experiments and trial here, something there. But it was never really easy to use and never entered the main branch. Now we have a couple of operations we can do now very fast without building matrices. The problem with sparse matrices is that matrix vector operations are quite expensive in terms of supercomputing. You have to bring the matrix from the memory, loading all the data, and you're not really utilizing your CPU. There are several possibilities to do a matrix vector product faster without computing and storing the matrix. And here we have some possibilities. As an example, I want to do a hybrid mixed method. Sigma is a local discontinuous diff variable. The U variable are the element polynomials L2 and facet polynomials. Okay, so we build the sigma space. I build the sigma space as a discontinuous HDiff space. What is essentially if it's a PDM, it's a vector valued L2 if we do the Euler mapping from the physical element to the reference element to the physical element. So we're using indeed a vector L2 now, where the mapping is a Euler mapping, like we do for HDiff. Element space L2, facet space. Okay. Okay, we are building now two binomial forms. One is a sigma times tau. The other one is a diff sigma times v, and the sigma n times v facet. Defining the binomial forms. And now let's have a look onto the element matrices. Okay. We can iterate over the elements. We can ask the finite element space for building us a finite element for this element ID. We can ask the mesh to giving us the geometry of this element. If we give these integrals to the binomial form, it maintains a list of integrators, list of symbolic integrators. We take the first one from the A binomial form, ask it to compute the element matrix for this element with this transformation from the reference to the physical element, and print the element matrices. Oops. Something not up. I think I have to restart this. Sorry. Okay, these are also element matrices from the sigma times tau binomial form. What do we see here? We have order 1, P1 elements, they are vector valued. P1 has 3, so we have 6 degrees of freedoms. And L2 uses an L2 orthogonal basis, which are diagonal matrices for L2 binomial forms, but they are systems of 2 components. They are 2x2 block diagonal matrices if you do a proper reordering. They are 2x2 block diagonal, but different for every element. They contain the geometry of the element. If you do the same for the integrals of the B-planar form, so the integral diff sigma times V, element from the first space, from the second space, building a mixed finite element space with a trial and test. Ask the integrator for element matrix here. What we see here is that all element matrices are the same. Independent of the geometry of the element, whether the triangles are deformed, you get the same entries. Also, geometric factors cancel out. So the mapping of the divergence, that is to the Euler, mapping of the U and the integral, the Jacobians, they all cancel out. And the same if you integrate it on the physical element or on the reference element. They're all nearly the same. The way we are dealing with orientation of edges, that we've built equivalence classes of elements depending on the numbering of vertices. So the precise term is that all elements are equivalent to a few elements, to a few reference elements. So we have a class of 2 reference elements, and every element is either equivalent to the left-oriented or the right-oriented element. Okay, so we can save a lot of memory by not storing the big matrix, but only storing the matrix for the reference element. They are all the same. Okay, let us set up a problem with this. So I define some 3D geometry. Same as above. Now I have order 5, 3D domain. Okay, vector L2, Euler true. And the new flag I have here is now geom-free is true. I have to know that the integrals are independent of the geometry. Then I can tell it to the planar form, and then it can do this, compute only the matrices for the reference element, and apply it to all elements of the mesh. Okay, we are creating 2 vectors from the matrix. B.mat gives us a matrix, either a sparse matrix or this optimized reference element matrix. And we're just timing the matrix times vector product. Time it from IPython. And we see that one matrix vector product takes something like 0.8 milliseconds. If we go back, if we do the same stuff without geom-free, it's about 20 times slower, I think, to remember. It's a timing takes that, so it's about 16 milliseconds per applications, about 20 times slower. So instead of doing the sparse matrix vector product, we can now do the multiplication of this reference element matrix with the vectors all together, utilizing dense linear algebra, calling blast kernels. I'm going to come back to geom-free to true. Okay, now we want to utilize also that the mass matrix is diagonal, or block diagonal, and this is provided by a certain mass operator provided by the L2 space. We can ask the L2 space or the vector L2, please give me your mass matrix with an improved implementation. You can give also a coefficient function, which goes into the integral, and this gives you also an inverse operator, also with an improved implementation. Okay, we want to solve this mixed problem, A, B, B transpose. Forming the Schur complement is essentially the Laplace operator. We are combining these operators. This fast matrix has also a transposed fast operator. Okay. So the good thing with this matrix tree is you can efficiently apply your operators. The drawback, it's not that easy to design good preconditions for it. We have something, but to keep it easy here, we're just using the identity matrix, project on the Friedhofs, and just run CG with this simple diagonal preconditioner. It takes a couple of iterations. I have increased the max steps, and the printing the rates would slow it down. But one iteration is very fast. And you see it's working for curved elements. And the example was set up like this. Oops, how do? You can. Oops. Now you can compute your own logo. Okay. It's also quite a new feature in NGSolve Python to access these fast matrix-free operator applications. I think there will grow some application on this, particularly designing preconditioners. So there's still ongoing research to precondition these matrix-free operators efficiently. And we will see another application of these matrix-free operators for time-stepping methods, where you don't build operators, you can do efficient DG time-stepping in Christoph's lectures later on. Questions so far to this part, to the last step, to the... If not, so then it's a perfect time for the break now. And we come back at point 4 for Christoph's presentations. Thank you. Yeah?
drauf? Einfach da hinten in den Nacken quasi, oder was? Wahrscheinlich, oder?
Genau, schaut gut aus.
Okay.
Und jetzt auf On.
On, okay.
Und dann nochmal testen, ob man das hört.
Test.
Ja.
Ja.
Und du möchtest Kamera weg?
Nee, ist okay. Rechts oben ist jetzt, ne? Rechts oben ist gut. Ja. Okay.
Pleasure to introduce Christoph Leonfeld, who is a very strong developer, the core team of NGSolve. Started from long time ago in Aachen. Started with HDIF conforming Navier Stokes models, and he went further on to XFAM, and he's giving the tutorials on time-dependent and nonlinear programs.
Yeah, thank you, Joachim. So yeah, it's 10 years now, a little bit more even, that I'm involved in NGSolve. Okay, so now the first part should be about time-dependent problems. So we have a few lectures on time-dependent problems, time-dependent scalar problems, Navier-Stokes, wave equation, and then going towards nonlinear problems at the end of this section. Okay, let me start with a very simple problem, parabolic model problem. So we have convection diffusion equation, time-dependent on the domain omega, and we have a given wind velocity b. Okay, so the usual stuff, loading some libraries, setting up geometry, so the unit square with the labels that you all know, bottom, left, right, top. Nothing fancy about this. And now we want to, after also seeing some bilinear forms and matrices that we're all familiar with right now, we want to do some time stepping. So I already define a time and some time step. Here dt is my time step. Okay, so the velocity field in the example that I want to consider is the following one. So this guy, it's a divergence-free velocity field. And yeah, it's this vortex essentially on the unit square. All right. Now what we want to do is we want to consider convection diffusion equation with that given and time-independent velocity field. Okay. Yeah, you all know how to set up bilinear forms and the corresponding sparse matrices. So what we do now is we do the corresponding parts for the diffusion part with a diffusion coefficient 0.01 here for the convection part. So it's B gradient U times V. And then we have a mass matrix here. And you see already something that we, I think, haven't discussed yet, but most of you might know already. So you can prescribe if a bilinear form is symmetric or not. That means if during storage of your matrix entries you exploit that you have a symmetry or not. So obviously for the A bilinear form you cannot do this because the problem is not symmetric. For the M bilinear form you could do that. However, we don't do this because we want to have the sparsity pattern of both matrices available, as we will see in a minute, in order to make linear combinations of matrices. So keep that in mind. So the symmetric flag is set to false here. Okay, so we want to solve a very simple problem with a very simple discretization. So what we want to do is we want to apply an implicit Euler method. So this is why we also need the mass matrix. So we have to solve the following problems. So we have mass matrix plus delta t diffusion matrix for the new time step and the corresponding right-hand side. We also write this in an incremental form. So we have this M star matrix times the incremental that we search for, which kind of indirectly defines our new time step value, is equal to the corresponding right-hand side. So what the first news aspect should be now is we don't want to assemble the M star as a bilinear form with an assembling afterwards, but we rather want to assemble M and A, what we did on the last slide, and we want to form a linear combination of those matrices. And kind of the thing where you have to be careful, that I also already addressed this, you have to make sure that the sparsity patterns of those matrices are the same, so that what we'll do in a minute also works as it should. So this is why both symmetric flags were set to 0. Okay, what we now do is we create a new sparse matrix, which should have the same layout as the M mat matrix. So this we can do with a create matrix, similar to what we saw with create a vector. So this gives us a sparse matrix with the same layout as the corresponding underlying matrix before. Okay, so if we do this, so what we see then is that the number of non-zero entries of all those three matrices, so M, A, and this new M star, is all the same. And if you take a look at the entries, okay, you could check that this is the same memory layout as before. Okay, so what you can do with a sparse matrix is you can actually access the entries of the matrix by calling this S vector, which returns you a vector, obviously, and you will see this vector has as many entries as you have non-zero entries. Okay, so you can also print the entries, and you can check that these are the same that we saw before on the slide. The corresponding first entries are 0.005 something, and this is then the first entry also of this vector. Okay, and this is what we use now to form this M star matrix by just using that the entries, so the values in the sparse matrix, that we can just linear combine them. Because we have the same memory layout, we will get the corresponding correct matrix. So what we get out of this operation here is the same as if you would assemble a corresponding bilinear form with the corresponding terms inside. Okay, then we invert this already to prepare the implicit Euler step. Okay, so we set up some right-hand side to make the problem a little more interesting. So this is the kind of two Gauss peaks that you have. So we have a blob at the left positive and a blob on the right negative. So sources and sinks that we want to incorporate in the problem. Okay. Yeah. So. Okay, we set up the matrix, the solution vector. We create a temporary vector, as I said, with the create vector part, and consider already the time loop. So this is now the time loop. Also nothing fancy if you compare this to the previous tutorials. So we just do the right-hand side for the incremental form. So we have A times UN times delta t with a minus, and then the corresponding right-hand side. We do the inversion of the M star matrix, and we add this up in the time stepping scheme. Okay, so if we execute this, this is kind of the evolution for a few time steps, where you can see kind of how, due to the boundary conditions and the source that we prescribe, that there's some nice pictures, essentially, coming from those initial values. Okay, so as we learned already, we can also work with base matrices and iterative solvers. So you could also think about not really creating a sparse matrix with new storage and new values for this M-star matrix, but just defining essentially the matrix through its operation. So here we have M-star alt for alternative, which just defines the matrix as the linear combination of the operators that you have. So you can apply matrix vector multiplication now, but you cannot call the inverse, so the sparse inverse operation on that. Similarly, you could try doing a corresponding Jacobi preconditioner just by setting up this as a linear combination of the corresponding Jacobi preconditioners of the individual matrices. And then you could solve this iteratively. I introduced a star here. Okay, and then the result, for example, for this preconditioned matrix is just the base matrix, so there's no storage involved in this matrix here. You could solve the same problem again. It's much slower now because, yeah, the iterative solver is not the best to do, just a Jacobi preconditioner, obviously, on the problem, but in principle, you can do this. You can circumvent setting up a new matrix. Okay, so this was a very simple starting point to solving time-dependent problems, and many components you already saw somewhere else. There are a few other details that I will not go into, so there's some supplementary material for you later on if you're interested. So how to kind of change the problem to have a time-dependent right-hand side, how to involve time-dependent boundary data, how to do Runge-Kutta schemes, so higher order time integration, or how to do VTK output for making videos or kind of pictures for post-processing. Okay, questions? Sorry, okay. So this just means that the loop waits until the picture is drawn in the GUI. If you put this to false, then it can kind of continue computing while perhaps the image that you get from the GUI is not up to date. So that might, if the computation is much faster than the visualization, might lead to some flickering and some weird looking pictures. But of course, it slows down your computation if the drawing is expensive, so that's why we have the flag. Other questions? Okay. All right, so next example is now incompressible Navier Stokes equations. So you already prepared from the Stokes tutorial that we had before. So now we only changed this slightly by adding the time-dependent, the time derivative. So we have a time-dependent problem now, and also adding the convection part here, which of course is nonlinear because the convection itself is the solution of the Navier Stokes problem. Okay, again, just importing the stuff. We again considered the same geometry that we already saw for the Stokes example. So this Schäfer-Turek geometry where you have a cylinder or a circle in the middle and you have some flow around it. We use the same labels as before, so we have different boundary conditions for the wall at this top and bottom. With a cylinder in the middle, we have inlet left, outlet on the right. Okay, so it sets viscosity to 10 to the minus 3. So relatively slow, but still moderate. We use a Taylor-Hood discretization here. So that's also something that we saw before. So we use order 3 vector H1, so component-wise in H1 conforming finite element space of order 3. For the pressure, one order less, and we put them together in a product space. Okay, so the vector H1 compared to putting the components together individually provides you the convenience that you have a divergence operator and the gradient operator as a matrix valued function. Okay, I should execute this, of course. Okay, so as initial value for the problem, we solved what we saw in the other tutorial already. We just solved the Stokes problem with the proper inflow profile. So this is just a little bit more extensive than what we have seen on the other tutorial, but it's the same result. So let's just do it. So we see if we set the boundary conditions here, we're all accustomed to that right now. So we have a coefficient function u in, and we set the a grid function component 0, so that means the vector h1 part of the product space. There we set the vector valued function, but only on the boundary part where we have the inlet. Okay, so this is kind of the function that fulfills the boundary condition, but nothing else. And okay, so we can also plot the profile. You can imagine that. And now we solve the initial Stokes problem. So yeah, this is again, A matrix is now the Stokes matrix. Yeah, so this is what you have in the integral there. So we later on only have to deal with involving the time derivative and the convection. So this is kind of missing here. For the right-hand side, yeah, we have an F linear form, which is just empty, so the ensemble does nothing but creating a zero-valued vector. We can set up the inverse of the Stokes, so this is just needed for the initial values, not later on for the time stepping. Okay, so we can execute this and we get pretty much what we would expect. So let's continue. Yeah, now for the time discretization, what we want to do here is, because we cannot yet deal with nonlinear problems, we will do this in a later on tutorial. We will do a very simple time stepping scheme which treats the implicit, the viscosity implicitly. So we have, again, such an M star matrix which consists of the mass matrix and the Stokes part of the bilinear form. And then everything else we put on the right-hand side, and that means the convection, so the nonlinear part, is treated explicitly. And we just do an implicit order for the implicit part, and an explicit order for the explicit part, so just the first order method. Okay, so you can also write this in incremental form. This is what we will do, but so this gives you kind of what we want to have. Okay, so this time, kind of alternatively to what we saw before, we assemble the M star matrix directly from the first place, but of course you could also just do the linear combination of the corresponding sparse matrices if you want. So we set up the corresponding M star matrix from the last slide, and now we set up the linear form responsible for the convection part, which you see here. So we have the gradient of the velocity times the velocity. So the velocity itself is, that was defined on the previous slide, is the vector h1 component of the product space grid function. So this is something that we can evaluate at every known time step. So this is for un, for the last time step, we can evaluate this. So we get a linear form that we can compute by a very simple assembly. In the next steps later on, we will see that alternatively to linear form, you could also use a bilinear form and an apply operation. So we will see what this means later on. Okay, let's just simply do this. So we have the example. So in every time step, we now apply this convection linear form. So this is what you see here. So this gives us this C of UU, so the convective part. We have, for the right-hand side, we also need the A times UN. So this is what you get in this residual vector that we created before, and then it's just applying the inverse of the Stokes matrix with a masked term. Okay, yeah, and then you could compute this for a longer time to get the very nice Kalman vortex street behind this circle. Okay. Any questions? Okay, so that's again a supplementary that I will skip. So you could also think about how to compute drag and lift forces around this circle. And this is kind of explained in a little more detail in the remainder of this tutorial here. Okay. All right, so this was comparably easy, I would say. So the components are more or less well known. Now we want to do something more related to explicit time stepping and operator applications. So a little bit thinking about what we can do in terms of performance. Okay, so let's consider the following linear transport problem. So we don't have any diffusion anymore, but we still have the time derivative on the solution u, and we have the convection part b dot gradient u for a given velocity field b. Okay, so the usual, we import what we need, GUI and so on. We consider the simplest geometry that we could have, so just a unit square again. Okay, then we make up some velocity field again. So this is this one. So it's just going up from bottom to top, and it's going from left to right with a kind of sinusoidal perturbation that you can see here. Okay. And now we want to solve the linear transfer problem by prescribing boundary conditions at the inflow, and it should obviously just be transported through the domain. So we don't have any right-hand side, so it's just a translation of the initial values. So the initial values are the following. So we use this if-pos coefficient function again. So this is the coefficient function which decides based on the first argument if it evaluates as a second or the third argument. And here we have this strange-looking function x minus 1/8. So that means whenever we are left of the 1/8, then we evaluate with the second argument, which is just a 0. If we are on the right, we evaluate the interior coefficient function, so which is this guy. There, now we have another argument which says essentially on the left of 0.625, we evaluate with this function 1 plus cosine something. On the right, on the left, we evaluate with 0. So that means essentially we have left and right of these two values, 1/8 and 5/8. We have 0, and in between we have something non-zero. Okay, and this should be transported through the domain. For the discretization, we consider an upwind flux that Joachim also mentioned before. So essentially, you do partial integration on your weak form on every element, because now we want to use discontinuous Galerkins, so piecewise discontinuous polynomials. So we get boundary terms, this guy here, so Bn times U hat. And the U hat now is the upwind flux. So we make a numerical consistent flux, so the same value for two neighboring sides. And we just take the upwind, so wherever the wind comes from, we take the corresponding value. Okay, so if we now want to solve the problem, so this is just semi-discrete. We didn't decide on what to do with the time stepping yet. And we could decide for two options. Either we solve linear systems when applying implicit schemes or explicit schemes. And of course, this makes a big difference in terms of computational costs. So in the following, in this tutorial, we only treat the explicit case. So we just want to do an explicit time stepping, just an explicit discretization scheme. For solving linear systems, this was discussed by Joachim, so you can take a look at the unit 2.8 on how to do this. And as an exercise, you could just try to do the same problem here just by solving linear systems. Okay, so that means if we want to do this, we take as the simplest discretization scheme an explicit Euler, and we have to solve the following problem. So we have, for the new time step, just the mass matrix, and on the right-hand side, we have to evaluate terms which depend only on the old values u on the right-hand side. Which are the old mass matrix, and of course the important part is the operator application that we will concentrate on later on here. So as the right-hand side we put 0 here, and as initial value also 0. Okay, so convection application. So there's the kind of first new thing that we want to discuss. So we define the operator C related to the bilinear form that we, or trilinear form that we saw for the Navier Stokes example before. We define a corresponding bilinear form here, but we give the flag non-assemble equals to true. And that means we don't want to assemble, we don't want to set up a sparse matrix for that operator, but we rather just want to implement the operator application with that bilinear form. And the bilinear form in NGSolve, contrary to what the name suggests, allows for nonlinearity in the first argument. So we can have the u gradient u in such a bilinear form, although it's obviously not linear. that obviously also only makes sense for applying operator applications. Now, you cannot set up a matrix if this is you have to linearize first in order to do that. Okay, so important thing from that slide is that we have this flag non-assemble equal to true. Okay. Then, as we saw before, we want to define the upwind flux, and this is, as was explained before, depending on b.n on every edge in a 2D. So if the flux goes from left to right, I take the left value. If it goes from right to left, I take the right value. So this is what happens in that line here. And then we set up just the definition of this form. And this reads as we are used to for setting up linear systems. Okay, so the important new thing also that we can do now, because we're not interested in setting up a matrix, we can also think about boundary conditions for this guy. So here we have, on top of what we had before, we can ask the question, if we are on the domain boundary, it might happen that Bn is negative, so that means we have actually an inflow boundary at that point. Yeah, so in our example, on the bottom of our domain, we have an inflow, and the question is now, what should be the evaluation of this upwind flux at that position? And there we can say, okay, typically we would say u other, so we go to the neighbor element, but now there is no neighbor element, and then we can prescribe the function that we want to prescribe instead. And this is now the u bound, so this was our boundary data that we defined on one of the first slides. Okay, so this is then the corresponding whole definition, so it reads like our the forms that we are used to. Okay, so then we set up the a grid function, and we can now apply to a vector from the corresponding space. We can apply this C is a bilinear form that we defined for c.mat, and c.mat times the vector is now not a sparse matrix vector multiplication, but instead it's just the operator application that is defined through this bilinear form. So we can do this. It doesn't do anything special. So which would not work is if we just do this without having this non-assemble flag. So if you just define a bilinear form, then it would ask for this matrix to be assembled. So it's expecting a sparse matrix. There is no sparse matrix. So if you say, okay, I don't want to have a sparse matrix, I just want to have the application, then you need this non-assemble flag. Okay. Then for the explicit order scheme, we also need the inverse of the mass matrix. And as for DG spaces, this is a very cheap operation because we have block diagonal matrices. There are special operations in NGSolve. So if you have a DG space, you can have the mass matrix operation and the inverse mass operation, as we saw before, just by calling those guys here. And again, the inf m is not a sparse matrix. It's just a base matrix which implements this operation of the matrix vector multiplication. Okay. So now to the time loop. So the time loop looks very simple now. We apply the convection operator. So this is CMAT times the old value here. Then we apply the inverse of the mass matrix. So this is essentially in one line here. And then we just add this to our, or we add the update to our solution. And the sign is just because the CMAT is now on the right-hand side has a different sign than the definition. Okay, so let's take a look at this. Let's perhaps turn off the surface vectors. So this is now what happens. Yeah, so we have this funny velocity field which transports the boundary values through that domain. Okay, let's also keep in mind how long this took. So this took 5 seconds approximately by doing this simple loop. So we can improve the situation a little bit by realizing that before in the DG formulation, we formulated everything with respect to element boundary terms. So here the integrals that involve the numerical fluxes, they are on the boundary of each element. So that means in principle that every term that we compute here has to be computed more or less twice, from the one side once and from the other side a second time. So you could think that doing a skeleton integration, so an integration which is based on the facets rather than the elements for those terms, could be a little bit faster. And this is kind of the corresponding formulation here. So it's the same, it's an identical discretization, just rewriting the element boundary terms in terms of facet integrals. Okay, so then we can just use the corresponding differential forms. So we have the facets that are interior. This is this guy here. We have the skeleton integrals which are on the boundary. These are these. You could also define this on parts of the boundary domain. So like inflow or outflow that are defined here as well. Okay, then you correspondingly define the new bilinear form, same way as before, where we now have also the boundary terms separately from the interior facets, obviously, and some of them incorporate the boundary conditions, others don't. Huh? Okay. So if you know a priori which part of the boundary is your inflow, then you could also use the version below, which essentially does the integration of the U-bound part in the inflow for the numerical flux and the U part for the outflow part. Okay. All right, so let's take a look at what comes out here if we apply this now. No. Our solution seems to be the same. It's a little bit faster, yeah? So 4 seconds, perhaps on your laptop, the difference is larger. Now we want to improve this further, and one of the reasons, one of the motivations is that if we have this other operation that is involved in the DG formulations, we always have to access neighbors, so we have to kind of always take a look at what the neighbor value is there. And one way to circumvent this is to first compute the trace of the piecewise polynomials that we have in our solution on the skeleton, and then work with that guy later on. Okay, so the idea is now that we have a finite element space on the skeleton, so that we already saw that. So this is the facet finite element space, and this should be, or this is now compatible to our volume finite element space, so it has the same order, and this is what we set up here. So we define the facet finite element space, which should represent the traces, and the VT is corresponding to the element values, so the discontinuous Galerkin space. And now the L2 space provides this operator, trace operator, which maps these from the volume finite element to the trace finite element. Okay, so let's have a look. So this seems to be consistent. So the volume finite element space has 2,160 degrees of freedom. The trace space only 1,160, and the operator corresponds to a matrix which is correspondingly, so trace dimension times volume dimension. Okay, and you can apply this like this. Yeah, again, this is a base matrix that you can just simply apply. Okay, now the question is, what is actually the result of this operation? So if I have a function defined on my grid, apply this trace operation, obviously I have on every edge in 2D in the mesh, I have a now double valued function because I have a trace from the left and from the right. What this does is it adds up both values. And this is why we kind of have to be careful in a minute. So what we now want to do is we want to write down the bilinear form, or this form C that we had before, by exploiting this trace. So now we assume we computed the trace operation. So now we have on the element, we have the element volume unknowns, and we now also have the traces corresponding to the same function. So there's the sum of the traces, if you are. Now we want to write down the bilinear form into several parts. The first one should only be element local and not involve this other operation. So no involvement of the trace operator. So it's a form that only acts on this VT space. The second part should now incorporate the fluxes, so the trace values that we obtained. So it's a function that works on that acts on the Vt times V space. And the third part is just responsible for the boundary conditions, so it's just acting on Vt as a linear form. Okay, and this is what we have here. So the volume part is stored in this C1 bilinear form, and then we have here now the fluxes through the facets in this C2 bilinear form. And here, so I wrote this in the comments, we now have the UF. So this is a mixed bilinear form, so we have different spaces. So the trial space is from the V space. So the V space is the larger space, which has both. It's the product space of the volume and the facet space. And the test space is just a volume space. Okay, so, and now the UF, so the values of this, from this trace find element space, are the sum of the two neighbors. So it's essentially U me plus U other. So if I want to have the value from the neighbor, I essentially just subtract my own value and I have the old U other. So that's what you have here. Yeah? So the upwind flux is if pos Bn, so if I have an outflux boundary, then I take my own value. Otherwise, I take the neighbor. So the neighbor in this case is UF minus UT because of this argument that I just made. Okay, and then I have to do a corresponding term for the boundary, which I put in the linear form here because it's not time dependent. Okay, so with that, I have now different bilinear forms actually on different spaces. I have to put them together to get one operator which maps from Vt again to a functional on Vt. And this, for that, I used the embedding that we already saw before once. So what I want to do is take a look at the last slide first. So we first apply the trace operator, which means I map my DG functions to the trace of those functions, to this facet find element space, and then have this embedded F, which just means that where's the embedding F? This is just this matrix here, so which blows up this again into the product space. Yeah, so we have the trace operation, it goes from volume to facet, and now this embedding F essentially just fills up the vector with zeros for the volume part. So this is what this embedding does here. So it just embeds the second component, so the trace values in this case, into the product space here, and correspondingly the same works for the volume guys. So there we have then the first component just fill up with zeros. So this MV operation now maps from my volume functions to this product space. Okay. And then I can sum up my total operator C by just saying C1.mat. So this is the operator application which acts on Vt already. And now the C2 acts on Vt if I compose this with this embedding V that we had before. Yeah, so the sum of those matrices now maps from Vt to Vt dual. Okay, and with that, we just have now, let's say, complicated way of writing down the C bilinear form, but hopefully it's a little bit more efficient. So what we now have is we pre-compute the terms corresponding to the boundaries. So this is this R part, and then the remainder is in this one-liner here. Yeah? So we have the application of the C operator, of the M inverse operator in this one loop. Okay, so let's see how this goes. Okay, so 4.8 seconds, not that much faster yet. So what can we do to improve this? Okay, before we go to improve this, there's one warning, so be careful with one-liners, because here you have on the left and on the right-hand side, you have the same vector that you manipulate, and if you do this in the wrong order, then you get something wrong. This is also the case here, although at first glance you might not notice this, but if you take a careful look at the boundary values, you will see that these are not so right. So you have a steep gradient here, which should not be there. You can check this in detail yourself. So if you want to be careful, just create a temporary vector to avoid this problem in the first place. Okay. Yeah, so this is the version if you're in doubt. So just create a temporary vector, and then you're safe with respect to that. So now we want to actually, the motivation was to get something faster, so let's try to get this guy faster. So what we do now is we exploit the geometry flags, the geom-free flag that we saw before. And for that, we again exploit that we have something geometry-free in our formulation. So what we want to have is that the bilinear form guy that we have here, so we freeze the wind to get something which is really a bilinear form, that this is geometry independent. So this guys with the hat, these are the guys on the reference element. So t hat is a reference element, and the corresponding other guys are functions or polynomials that you evaluate on the reference element. And actually this here holds true if we if the mapping for the evaluation of functions on the physical element is just a direct mapping, so we just evaluate a function on a point x by evaluating the function on the reference element on the corresponding reference point. So this is for u and v, and then for the w, so for the wind, we use the Payola mapping. So this is the guy here. So we involve the shape and the transformation from the reference element to the current element also in the mapping. So if you have this, then you have this geometry-free property, which means that these integrals are all the same. Of course, the w now, in contrast to what we saw before, the w will be different on every element. So we will not have that we just have 6 or a small number of same matrices. However, the evaluation that we need, so the gradient of u and the v hats, the corresponding integration points, so the evaluation at those integration points, they will all be the same. So this allows us to at least prepare some intermediate computations for this step. Okay, and this is, without going into the detail, what we want to do here. So the first thing that we have to do in order to have this, we have to put our velocity into an HDiff conforming finite element space, or another space which has the Payola mapping. So we could also use the L2 with a Payola that we saw before. So here we do this with the HDiff. So we get a corresponding function which looks essentially the same because the interpolation is good enough as the exact field. Okay, and then we apply the same that we saw before, same bilinear forms, C1, C2, and so on. Now we added the flag geometry free equals to true in the constructor of those guys. Okay, now if we do this, we are now at approximately twice as fast, so it's 2.5 seconds. So this is good. Questions? Okay. How's the pace? Am I too fast? Too slow? Okay, so I'm perfect. Probably not, but let's see. So now we want to continue with a similar aspect. So we're still in the business of operator application and getting this fast. And now we compare kind of the simple version against the tuned version in terms of this operator applications and so on. And now the application is acoustic wave equation in time domain. So we have a vector valued function u, so the velocity and the pressure, scalar valued p, and you have this standard first order formulation of the wave equation. Okay, so we consider simple geometry, so unit square, you know it already very well, and we want to formulate a formulation which is structure preserving in the sense that we have the same bilinear form involved to discretize the gradient and at the same time the divergence of u. And this is this bilinear form here. So we again use discontinuous polynomials, order k plus 1 for the pressure, and order k vector valued for the velocity in every element. And the formulation is obtained by essentially formulating this. So, for example, if you start with the divergence of u, you do partial integration, you have to put in some numerical flux. And here the numerical flux, we just use a centered approximation, so we have energy conserving scheme, which is perhaps not the best, but for our purposes here, it suffices. It's a reasonable guy at least. So order 6 polynomials for the pressure, order k plus 1, so order 7 even. We have this flags all doves together, which means there's no low order, high order separation in the numbering of the degrees of freedoms. We use a discontinuous vector L2. So vector L2 is the analog to the vector H1 that we saw. So it's a vector valued version of the L2 function. And now we have the flag Payola. So we have the Payola mapping that we need in order to get something which is geometry free as we saw before. Okay, and we put this together in a product space. Okay. Yeah, so just a remark again on this Payola flag. So the Payola flag essentially means how we evaluate function on the physical domain depending on the function on the reference domain. If you don't do any flag, so no Payola, then you just get the direct mapping, so the standard one. If you do Payola true, then you get the Payola transformation, and you can also do covariant transformation if you're having some H-curl, some Maxwell problem or something like that. Okay, so this then goes accordingly. Okay, so now we want to work on this product space, and we will need for the explicit time stepping that we want to use, want to apply mass matrix inverses, again these fast operators that are provided by the spaces, and now we set up corresponding operators for the blocks, and this is what you see here. So we want to have this inverse operation just in the first block, and we obtain this by using the inverse operation on the pressure space, and then combining this with the corresponding embeddings from the pressure to the product space. Okay, so the same accordingly for the velocity, so nothing fancy here. And then we define the time loop, where this time loop is now depending on the operators B and B transpose. That should be some operator which provides some operator applications or matrix applications. And then what we see here is a symplectic Euler discretization, so where we essentially just apply the minus B transpose with the inverse of the mass matrix of the pressure space times the solution U. So this affects then the corresponding part because of these embeddings that should be involved. So once we updated in this case, the pressure, we make an update of the velocity with the new pressure, so that's a symplectic Euler scheme. And for fun, we also implemented kind of the backward step, so we can put this time loop that we have here, not going forward in time, but backward in time. Okay, so this is the run function that we'll use later on to evaluate the performance of different formulations. We prescribe some initial initial values for the pressure. So this is kind of the pressure initial condition. There's so 0 values for the velocity. So this is kind of this blob which goes to the interior as well. And yeah, we want to take a look on how this evolves. And the first simple version that you could do is just write down what we know already very well. So just write down the bilinear form, set non-assembled true, and just call the run function with the B mat and the B transpose mat. So first we solve the same problem forward in time, and then the same amount of time backward in time. So that's what we'll see here. One moment. In those two blocks. So not that fancy. So now it's going 4 seconds forward, 6 backwards. If you run it multiple times, it should be approximately the same. So this is the amount of time that this approach takes. And now we want to see, can we improve that? And for that, we want to use the trace operator and assembling of B. Now we have a linear problem, so we could hope for assembling the sparse matrices and applying those. Perhaps this is faster than applying the operators only. Okay, for that we define again the trace operation that we saw before. So we can go quickly through this. Okay, so corresponding basis functions now for the pressure space is this P hat. Okay, and we have P and V. So now the splitting is the same as before. So we want to have a splitting into one part which just involves element local quantities and one part which involves the coupling between the traces and the interior. So this is B element and B trace parts where we write down what we had before. And again, P hat is the sum of the two neighboring traces. And this is kind of the way you write down the same formulation, so the centered flux approximation that we had before, now in this, with those variables. And you put together a fitting operator by applying the corresponding embeddings from left and right. Okay, so let's see how this performs. So it goes forward for some time. Goes backward for some time. Okay, so this is not even faster than what we had before. So version 3 is now what we now did not exploit yet is the fact that we have the possibility to exploit the geometry-free integrals. So we have the Payola mapping involved, and that's kind of what we want to exploit now in the last step. So this is now the same setup as before, so trace operators and so on, but now we add the flag geometry-free here. Okay, and this is what we get for the assembly. So now that's the important part. So now we assemble the matrices, but these matrices are represented by just a few element matrices due to these classes that Joachim already discussed. Okay, now the application. So that's what we want, what we are interested in now. You see, this is now almost a factor 10 faster than what we had before. Yeah, so here we really benefit from this geometry-free combination with the assembling in the matrices. Yeah, so in the last unit, in the last tutorial, we also used the geometry-free, but there we could only exploit this for setting up the integration rules and pre-computing the operators. The wind was still depending on space, so on every element, obviously. Here we really have that there are just a few element matrices which we can use for all other elements at once. Okay, questions? All right, so then let's see. I'm not that good in time. So I will just say that there is this tutorial 3.4, which is in the spirit of the others, seems 2 tutorials that we saw. So it's again about operator application, explicit time slipping, but now for a nonlinear problem. So here's a shallow water equation, explained how the fluxes look like, how you do with electric discretization, how you can do that. You can click through that. There's also a video. I will skip this here. So the only, I think, new component that you can learn from this tutorial, except from having something complex to work with, is the fact that, again, we use the bilinear form expression for something which is nonlinear in the first argument. Okay. This is also something that we can skip. Just to mention what it does, it's again solving a convection diffusion equation, but now on the surface of a problem, so of a geometry, and not in the volume. So that means that you can take a look at how to define operators, meshes, function spaces, and so on, only on the surface mesh in NGSolve. So the last minutes that I have, I would like to spend on the last three parts. So the first one is now a DG-HGG splitting. So 30 minutes, huh? Yeah. Okay, so what is the idea now? So before, in the Navier Stokes example, we already saw a very cheap or very simple way to set up a timeless stepping scheme, where we decided to set up this M-star matrix for the instationary Stokes problem and do an explicit scheme for the convection application. Now we want to do something similar and now improve in certain aspects. So here we want to change the spatial discretization. So we want to go away from the H1 conforming setting that we had in the second tutorial in this section, but we rather want to go to something DG-HGG. I will explain this in a minute. And furthermore, we want to also do something a little bit different in terms of the operator splitting, or in splitting these operators in terms of explicit and implicit. So what we want to do is a Yanenko type operator splitting. So we solve this problem. So the operator here stands for the Stokes part of the problem, and the operator C for the convection part. And what we want to solve now is we want to solve in a series. We want to first solve a problem that does not involve the Stokes part, so just the convection part for some time step Tn to Tn plus 1, which gives us an intermediate solution. And then starting from that, we apply another time step from Tn to Tn plus 1 for the implicit solution of the unsteady Stokes problem. Okay, so this is not the best discretization that you can do, of course, but this tutorial is meant to show some components based on this discretization. Okay, so for the discretization, we also want to do something more fancy than just Taylor-Hood. So we use something which is HDiff conforming, because HDiff conforming is very cool. It's very nice, has very nice properties, and especially for Stokes and Navier Stokes, there are very nice properties which lead to certain robustness and flexibility of this method. So what we want to do is a DG formulation based on an HDiff conforming finite element space. I want to combine this with an upwinding with respect to the convection. And because of we want to solve the linear systems for the Stokes part, we don't want to use a standard DG discretization, but as we learned before, doing something like an HG discretization is cheaper. This is what we want to do in this tutorial here. So geometry is the same as we've seen before already. So this is this Schäfer-Turek geometry. And now the HDiff finite element space we also saw. The overall discretization for the velocity is, however, a little bit more complicated. So we now have an HDiff conforming finite element space. So we are non-conforming with respect to the H1 regularity that you typically have in a Stokes, and especially in Navier Stokes problem. So what we have to deal with is incorporating tangential jumps weakly. And this is what we do with a new space, which is called the vector facet space or tangential facet space, which are polynomials that are just defined on the skeleton, so just on the facets, and are in tangential direction. Yeah, so like the trace of an H-curl conforming finite element space. Okay, and the corresponding fitting pressure space to that is just obtained by taking the divergence of the space, which just means you take a piecewise polynomial discontinuous 1 degree less. Okay, and this is the space. So we have an HDiff space of a corresponding order with corresponding boundary conditions. You have a vector facet AV space of the same order. You have one order less for the pressure space, and you put them together in one product space. Oops. Okay. We also have here the tangential projection involved, which is just on every facet subtracting the normal components, which we'll need in the formulation. So what you see here is now the formulation of the viscosity and the divergence constraints put in one bilinear form. So if you just consider the first integral and the last three ones, this is the vector-valued version of the interior penalty, or the hybridized version of the interior penalty method that you already saw in Unit 2.8, where Joachim discussed DG discretizations, and then you have the corresponding gradient of the pressure and the divergence constraint in here. Okay, so this is what we define here. So think about this in the H1 conforming world. This would just correspond to those three integrals here for the Taylor-Hood, and these guys here are now necessary because we don't have the tangential conformity anymore. Okay. Yeah, we set up the corresponding mass matrix for this guy, set initial conditions, solve the Stokes problem. So this is what we know already. And now the question is how to do the time stepping. And for that, we wanted to have first solve a problem that just involves the convection, so not the Stokes parts. And we want to do this actually on the DG space. So there's no point in doing an HGG discretization for this because it's completely explicit, so we don't have this drawback of additional couplings that we have in HGG methods. Okay, so we want to apply a method as before, but we have to make the spaces that we use compatible. So we have to map from the HGG space, so this product space out of three functions, we have to map this into an L2 space, which is simply what we saw already in the other examples, and then apply the operator there and project back into the other space. Okay, and here we can do this by formulating mixed bilinear forms for the transfer operation, or you could similarly do something like the L2 convert L2 operator that we saw, that we also discussed in a minute on the slides. But kind of the straightforward way to do this is the following. So we have now the vector L2 space, which is the space in which we want to apply the convection operator. And then we have this mixed bilinear forms, which involve functions from the product space of the complicated Stokes discretization and the L2 vector L2 space. Okay. Yeah, we apply those two and want to apply standard convection discretization by upwinding. And we also know that we have, as the velocity field, we have this HDiff conforming velocity already, which is pointwise divergence free because it's a solution of Stokes or unsteady Stokes problems. Okay, this is how it looks like. So we just have, so these lines here, so the whole block corresponds to the vector valued version of the upwind discretization of the convection. So this is something that we know already from before. And now we have a new matrix operator, or a base matrix operator, which should solve this convection problem for a certain amount of time steps. So we want to solve for tau, so for Tn plus 1 minus Tn. We want to solve the problem, and we allow to apply several sub-steps to go from the one to the other. For example, to meet stability conditions. So in the constructor, we essentially just define some functions, for example, the mass matrix, the inverse match matrix operations, and so on. And then in the actual operation, we first, and this is kind of what was important, so the first line, the input of this is now an HDiff, or it's actually from this product space, from the Stokes discretization, it's a vector x. And now the BF mixed matrix is now the application of this guy from the previous slide. So here we defined this mixed bilinear form. So the result of this application is now functional in the L2, in the vector L2 space. By now applying then the mass inverse of this space, we essentially have the representation of this HDiff vector as an L2 function, or vector L2 function. So this is the result here. And then on this, we just apply the standard, or the simple explicit order scheme in a similar manner that we saw before. Yeah? So we have the convection application, we have the inverse mass matrix, some sub-time steps, and so on. And then if we have the solution after several time steps in the L2 space, which project back into the HDiff or in the product space, which is then happening here with the BF mixed transpose. Okay, so putting this now together, we set up the M star matrix for the unsteady Stokes part of the problem, and the overall time loop now takes this form. So we have the propagate convection operator, so this was the base matrix that for which we defined the matrix vector, or the operator application. We set a number of sub-steps that was defined before, I think 10 or something like this, and now this is the overall application that we get. So we have essentially applying this 10 sub-steps, obtaining a residual vector from that, and solving the unsteady Stokes problem for this. So it's an implicit order for the Stokes part, and several steps of the explicit order for the convection step. Okay. And with that, we can now solve the problem as before, with the benefit that the stability restrictions are a little bit better than if you would just apply the IMAX scheme that we had before. Okay, so the idea of this tutorial was essentially to discuss the operators between the different spaces. And instead of doing this with the mixed bilinear forms, you can also do this with the convert L2 operator that also Joachim mentioned before. So this is what you have here. So you can directly write down this operator going from the HGG space, or the Stokes discretization space, to L2 by first applying the embedding. So just take the HDiff part of the whole vector and then convert the HDiff function into an L2 function. So this is what gives you that operator here. And then the corresponding new multiply operation of this propagate operator takes this form, where we essentially just have now the HDG to L2, which replaces the mass matrix inverse and the mixed bilinear form applications, and the same also for the result vector here. Okay, and then we can do the same as before, so continue with a few other time steps. All right, questions? Okay. So these units, last 4 units, were lots of units for time-independent problems and operator applications, and how to kind of deal with them, how to make them efficient, how to work with different spaces. Now the last 2 units are again more on solving things implicitly, also essentially stationary problems and nonlinear ones. So let's start with a simple nonlinear PDE. So it's a model problem. You have this reaction term, which is U cube, and you now want to solve this guy with some kind of Newton method. And what you can do for this is you can write down the bilinear form again, not bilinear in both arguments, but you can directly, oh, this is again wrong. I think this was wrong at the last user meeting already, but okay, so you can directly write down what you would like to have. So here, let's say this is your nonlinear form that you want to have in your discretization. So it has a nonlinearity. So here it's 3 to the times u to the cube. Here it's 5u squared. It doesn't really matter. You can just write it down as such. Yeah, so you write down the bilinear form with that expression, and obviously it's not a linear part anymore. So we have to linearize, and we can apply Newton's method for that. So if you want to do that, then you compute a linearization and solve for the update of the linearization. So you all know Newton's method, I guess. So this is what we want to implement here. So, and this is the implementation, or a very prototype typical implementation. You have a number of iterations. First, what you need to do is you need to evaluate your form given your argument. So you have essentially just a linear form left if you replace the u's with your current values GFU, so that's what you need. This is the apply operation. And then there is the assemble linearization, which allows you to linearize your form around a linearization argument. Okay, and then you solve for the linearized. So here we set up the sparse matrix corresponding to the linearization argument. You can solve for this guy and update in the Newton's method. Yeah, so it's relatively simple. So the key point is that we can do this assemble linearization where you don't have to do this by hand, but this will happen automatically. So it will essentially differentiate your expression that you have defined in your bilinear form here with respect to your argument u. Okay, so let's see. So the very simple problem. So we now apply the Newton solve, and you see, okay, after only a few iterations, the Newton converges. You can also now see that there's something shipped with NGSolve, so you don't have to write your own Newton solver. You can also take the Newton solver from the solvers module from NGSolve, and that has a few arguments that are more or less obvious. So you prescribe your form, your grid function that you want to work with. You prescribe which theoretically degrees of freedoms you might have, and so on. All right, so solving the same problem now with the NGSolve implementation gives you the same solution actually, and also the same amount of iterations. Okay, not surprising. So if you're interested in a trivial problem because everything is too complicated so far, take a look at this. I will skip it. Let's go to Navier Stokes again. Now we want to solve Navier Stokes stationary, where we have nonlinearity here in the convection part. And we want to solve this problem. We put directly boundary conditions everywhere in our domain. So in order to fix the pressure then, to have a unique solution for the pressure as well, we added a Lagrange multiplier here to have an average pressure 0. Okay, so then apart from everything that we learned before, the only new stuff is again that we have a nonlinear form here that we put in. Apart from that, it's a Taylor-Hood discretization that we see here, and the components are well known. Perhaps one new thing is this number FE space is just a representation of a global scalar that you can use to introduce this into your variation formulations. Okay, so that's what we do here, and now we solve the nonlinear problem. So physically, this is a driven cavity problem because we apply the shearing on the top of the domain. So that's what we do here, and then solve the Newton problem on this. Okay, so this gives us, this is the pressure, for example. We could also take a look at the velocity field. This is for a relatively high viscosity. So let's make it more complicated. So we decrease the viscosity, solve the same problem. Again, we need a few iterations. So now it's one iteration more. It's obviously more convection dominated now, but still not too challenging. So let's decrease it further. So this is what you see here. So now you have Newton iterations, and it gets more and more, and actually it's not converging anymore. Okay, so this is the kind of the first case where this example Newton implementation doesn't work. Okay, solution breaks. What you can do, however, is you can use the NGSolve implementation and then add a damping to your Newton scheme, for example. So that's what's happening here. So reset the initial guess to just be fulfilling the boundary conditions, and then we apply the damped Newton shipped by NGSolve, and you see that it takes, of course, a few iterations, but it converges, and you have something like Reynolds 1000 problem solved as well. Okay, questions? No? Okay. So then, last.
Just a small hint, the person behind the Newton is like Michael Nonlinear.
Yes. Okay. Okay, then last part is nonlinear minimization problems. So now you want to formulate your problem as a minimization problem. So you have a functional like this guy. So this leads to you have essentially u to the 4 here. This would be equivalent to solving this nonlinear PDE by taking the corresponding derivative, setting it to 0. However, we want to kind of formulate this now in NGSolve directly as the minimization problem as it is in the first place. Okay, and also want to apply. Okay, so standard geometry, unit square. Something's wrong with my setup. So now what you can do is variation, I guess. So you can do several things. Now you can define just this form that you want to minimize, and then you can put this into your bilinear form, and you can ask the bilinear form to do several things. First of all, you can ask to evaluate that cost functional, so the energy. Here, then you want to apply. So what is the apply is essentially the derivative of that cost functional with respect to your state u. So that gives you a linear form that you get by calling the apply function to that bilinear form then. Or you can also obtain the second derivative, which corresponds to the assemble linearization in NGSolve. So here you can write down variation. So this is the problem now put in very symbolically into your bilinear form. Okay, and this essentially is equivalent to putting the corresponding PDE problem, which is written down here as a nonlinear example, but we do it this way here. Okay, and now we can do a Newton iteration for the minimization problem, which takes essentially the same version as before, with the corresponding different interpretation of what is the A guy here. So this is again the implementation of that. So we see that without actually having different, without having defined, or now we take the variation which replaces our nonlinear definition. We can just implicitly deal with that as the corresponding guy from the linear version. So we have the apply, we have the assemble linearization, and we can do the Newton iteration again. Okay, so we can solve the previous problem with the nonlinear Newton guy. Okay, with a few iterations. We can also evaluate the energy after each step to see if it really decreases. Okay. And again, I think probably also due to Michael, there's also a version shipped with NGSolve, so you can solve the same problem now just with NGSolve, and you get converging scheme. Okay, so because we are close to the end, let's take a look at a few nice examples. For example, nonlinear elasticity. So here the energy is not that trivial anymore. So we have this guy here depending on your deformation. So V is the deformation, D is then the gradient of the deformation, and corresponding to that you get corresponding stresses that you can put in some model. Here we have a nonlinear model for that we can just put into NGSolve. So we define a geometry. This time it's not the unit square. You might be surprised. This is just a rectangle this time. And okay, so we fixed the boundary conditions. We'll see this later on the left side, and we'll apply some load in the volume. Okay, so we will define some coefficients. And the forces, as I said, so this is not that fancy. So this is now the part where things get a little bit more complicated, to write down at least. So we define now the energy as variation, and we put in that complicated expression that you see here, which involves the different terms. So what do we have here? So we have the identity matrix. Okay, this is easy to understand. We have the deriv, or you could take the grad, actually. So this defines our F matrix. We have the F times F transpose as a C. Okay, and the neo-Hugesian model that we have here now depends on this C. You can easily imagine that now the evaluation tree of that coefficient is very complicated and involved, so it makes sense to call the compile here to simplify the expression that we get here. Okay, and then the loading comes from the force that we have in the expression here. Yeah, so the expressions are complicated, but if the model is clear to you, it's simple to write it down in NGSolve. Okay, so then we can solve that problem. So let's take a look at what is happening here. So we solve actually a series of these nonlinear problems by increasing the load step by step. So we don't apply the full load at once, because then it might be difficult or impossible for the Newton scheme to converge. Instead, we do this here in a loop over 50 substeps. Okay, so let's take a look. So this is what you see. You have a few Newton iterations for every load, and then you increase the load step by step and end up with this hanging bar. Okay, another example is an Kahn equation that I would actually skip if that's okay. Or should I still do it? Yeah, we are over time. So more importantly, do you have questions? Perhaps if you have questions, then we could perhaps address those. No? Okay. Yeah, okay. I mean, okay, so what we do, we again have an energy. Now it's coming from a phase separation modeling. So you want to have a function which is essentially zero, essentially constant. It should take the values 1 or -1. So the energy penalizes gradients, so that leads to essentially being constant. And it penalizes to being away from 0 or 1. So that's what you have here. Okay. Yeah, then we do the gradient flow of this, so an L2 gradient flow. So that means we have an unstated problem from some, the variable v describes the mixture of certain phases, and this kind of a demixing of those guys corresponds to the minimization of the energy of that process. Somehow, okay. Don't click on formulas. Okay, and the discretization is just a simple time stepping for this implicit Euler again, where every part of the implicit Euler's gap is again a nonlinear minimization problem. So this is what you see here. So in every time step, we want to minimize this energy, where we have additionally this penalty on the inertia, if you want. Okay, so we put this all into this one large code block. You have the terms that we just wrote down before, and yes. And the deformation is from the last part and not really meaningful, so let's move those. Okay. Okay, so now this is more meaningful. So we have this is initial value of this the solution. So it's a certain this describes a certain mixture between 1 and -1, and some smooth transition between that. And now this Alan Kahn model describes the phase separation and should lead to the fact that we have values -1 and 1. And the transition between those values -1 and 1 should be relatively sharp, depending on the parameter that we have in the energy functional. Okay, and then we do this now for 50 time steps again, and solving in each time step this nonlinear minimization problem. And what you get is this. Yeah, so the function takes values which are approximately 1 or minus 1 in this plateau region, and you have a steep gradient in between. And there's one last thing that which is not on your tutorials, but which was on Jay's part, which I briefly at least want to try to explain again. So the question was for the BDDC, how to get this picture with the connected dots, the vertex, the high order function which are connected at the vertices, but discontinuous otherwise. And there you have the postscript block, so you can take a look at the unit 2, 1, 3 at the end, so you all have this there already. And I briefly want to explain how this is related to the nonlinear minimization problem, which Joachim obviously formulated here. So we have the space U, space VHO disk, so higher order discontinuous. We have a low order space V low order continuous, and we have a space V low order discontinuous. This is what we do in this block here, so we just create those spaces. And the purpose of the space is the following. What we want to do is we want to solve the following nonlinear minimization problem. So, oh, sorry, this should be, of course, norm squared. Yeah, sure. Okay, doesn't really matter. Okay, and the right-hand side of the problem is a 1, so this is essentially corresponding to this. So you want to minimize that. Let's take a look at the first part. You want to minimize this. This corresponds to solving the following PDE here. So just a Poisson problem with the right-hand side 1. But we also add the Lagrange multiplier here, which says that u minus the low-order function should be 0 with respect to this test space lambda. Okay, and this is what we have now in the formulation, and this is evaluated at all the vertices. So what we essentially saying here is that at every element, at every vertex of every element, we want to have that the high order function and the low order function coincide. So these are exactly the lambda space has 1 degree of freedom per vertex per element. Okay, and this is what we can constrain now with that. And this is now written in this one nonlinear minimization problem here. So we have the evaluation of all the vertices of all elements. This is written down here in this dx and then element VB B boundary. Yeah, so this gives us the vertex evaluations of the Lagrange multiplier lambda and the U high order and the U low order. And apart from that, apart from fulfilling that constraint, we just solved the Poisson problem. So it's a minimal energy extension of those vertex values. So that's how we got that picture. So let's see. So that's how the picture got created. Okay, so this was it from my side. Any questions? Yeah, sorry. So the former version was the symbolic energy, and I missed to translate this in the notebooks. I just did this today, so that's why you still have symbolic energy written down there, but it does the same thing. So the variations need, of course, the differential form. The symbolic energy needs the flag to know if it's volume or whatever integral, but they have the same purpose. Okay, anything else to add? Then, if not, then Joachim takes over.